So today I will be talking to you about some of the research that we are just getting started on to redesign hardware architectures, particularly for these hyperscale web services. So there's a lot of parallels with what we are trying to do here and the work that has been going on at Crossroads. So while I will share some of the work that we've already done, I'm more excited to share some of our ongoing and some of our future ideas to see if there might be an interest in some potential collaborations and so forth. So feel free to interrupt at any point during this talk with questions, comments, especially on the ideas that we're excited about doing going forward and things like that. Okay, so let's begin our story with Oliver here, who from the time he was born has been able to use web services like Facebook, Google, and Amazon. So these web services, they run across hundreds of thousands of servers in a data center, which is called running at this extremely large scale or running at hyperscale. So today, these web services, they are composed of microservices. So let me show you a simple example structure of these microservices, right? Now, let's say, you are a user and you're sending a request to YouTube. Maybe you want to watch relevant videos for CMU, ECE or something. Now your response needs to come back very fast. Typically, this has to be of the order of a few hundred milliseconds so that you as the user can see that response almost instantaneously. Okay, so what typically happens is your request, it first goes to a front-end microservice which parses that request. It might then send that request to a hashing microservice, which extracts information about relevant videos. It might then send that request to an ads microservice, which figures out some advertisement videos to show you along the way. And then it might send that request to a caching microservice, which will fetch the relevant videos. And then it might send these videos to a ranking microservice to rank them in a suitable order. Now, this is just a simple structure of YouTube that I'm showing you here. But in reality, there are numerous such microservices that are interacting in extremely complex ways. Does this structure look familiar to you? So these microservice interactions, they actually resemble the Death Star. And so, of course, there are all of these interactions going on in the background, but Oliver here is just blissfully unaware of all of these details. In fact, most of us are like Oliver, where we take these web services for granted and we rely on them without even thinking too much about it. Like some of you might be using Gmail to check your email right now. Although, I hope you aren't doing that. And we only expect these web services to continue to grow to more complex applications like, say, self-driving cars, AR, VR, conversational AI, and maybe even the next time machine, who knows? So I'm here today to, first of all, burst your bubble by telling you about how we cannot realize these complex web services of tomorrow because of a variety of problems that I will describe to you. And then I will build you up and I will give you a new hope by describing our research that addresses these problems to enable these future web services. So over the past few years, there's been this radical shift in hyperscale computing because of two important trends. The first trend is that of hardware performance scaling, where from the 1980s to about 2005, performance would scale exponentially, and we saw like 1,000x improvement. But since then, scaling has all but stopped. There's been only like a 5x performance improvement since 2005 because of the decline of Moore's law and Dennard scaling. But on the other hand, we see that these web service requirements, they have actually increased in a tremendous way. So these web services, for example, they're starting to be used by billions of users. They have data rates that are growing exponentially. And also these services are performing more and more sophisticated operations by the day. So for example, they're performing personalized machine learning driven recommendations. So clearly, modern hardware is at a point where it can no longer meet this rapid shift in hyperscale computing requirements, which means that there is now this urgent need to redesign hardware architectures fundamentally from the ground up to deal with all of this, increase in data, users, and also service functionality. So in order to redesign the hardware from the ground up, we should first take a look at what do today's servers even look like, and what are the fundamental problems associated with them. So here on the left, I'm showing you this simplistic view of a server blade that's used in data centers today. So you know what you have the CPU that's owning the memory, and that memory is operated at hardware speeds. And all of these IO devices, like say the network, the storage, all of these different types of accelerators, they are accessed by these legacy software stacks and interfaces that move all of this data around. Now, take a hard look at this architecture on the left and think about, does this look familiar to you? It should, because the fundamental architecture is still pretty much the same as the desktop PCs of the 1980s, where again, you have memory operated at hardware speeds and owned by the CPU. And again, you have all of these IO devices accessed by these legacy interfaces and abstractions. And I mean, of course, the processing frequency has gotten better and all that, but the fundamental architecture is actually pretty similar. Now, of course, that was only a simplistic view. There's this glorified server blade today that looks slightly different from the simplistic cartoon that I showed you before, where maybe now, you might have a smart NIC with its own compute capability and its own memory. Maybe you have some accelerators, like say a GPU, for example, which has its own memory. But again, the basic architecture is still pretty much the same as the desktop PCs of the 1980s. In fact, with this glorified view, the fragmentation of silicon, particularly from that of these memory resources, that has only gotten so much more worse here, like as I'm showing you with these red blocks. And this has resulted in a lot of data fragmentation, which has resulted in a lot of consequent data movement and transformation overheads. So now, if you look at what these extremely beefy server blades, by the way, if you look at what they are doing in the data centers today, they're basically doing simple things like saying that, oh, the data needs to go here, or the data needs to go there. They're behaving as this orchestrator of data in order to have the data shipped around to these various devices and transformed into a form that is suitable for each of these device requirements. So to minimize these data movement and transformation overheads, our goal is to fundamentally rethink data center hardware architectures from the ground up, where we transition from a compute-centric to a data-centric architecture. So something that roughly looks like this cartoon here, where memory or data elements, they are the central entity along with their closely coupled transformation engine. And all of these different compute elements, they are at the periphery. And this, we think, is the first step towards building such a data-centric architecture. So the first thing that we are trying to do is we're trying to go down this path of identifying what this data transformation engine should even look like, where we are trying to see and identify the types of data center operations that are frequently transforming different types of data as and when they're sending and processing requests to different devices, different microservices, and so forth. And the fundamental question that we are asking is, among these different types of data center operations that are frequently transforming data, what are the ones that are such big heavy hitters that they deserve their own place in the hardware and they deserve to be ossified in the hardware? So in this talk, I will first tell you about how we started off by characterizing these data center applications to analyze the types of these data center operations that frequently transform data and possibly, deserve their own place in the hardware. Next, I will talk about this analytical model that we built to identify, what is even the right way to accelerate these operations in the hardware. And finally, I will tell you about some of the ongoing research in our group, and some of these are pretty broad, open-ended questions that we're asking towards building this data-centric hardware architecture. So I guess I will move on, starting with the characterization. To answer this first question of what types of data center operations frequently transform data and consume the most cycles across the global server fleet, we started off by characterizing 7 important Facebook's production microservices, which actually are some of their heavy hitter services and run globally across their data center fleet. So Web, which is Facebook's, or I guess Meta's front-end microservice, Feed 1 and Feed 2, which are a couple of microservices that go into Facebook's newsfeed application, Ads 1 and Ads 2, which are advertisement-related microservices that very typically perform things like ads ranking and indexing operations, and Cache 1 and Cache 2, which are very similar to modern-day key value store services. So what we did first is we went about characterizing the operations performed by these Facebook's microservices. So in this graph here, I'm showing you the CPU cycle breakdown spent in various types of these microservice operations. So from this graph, we see that most of the microservices spend only a small fraction of their cycles performing their main application logic, which is this blue portion. So typically, what is this? This is something like machine learning inference. So ideally, what would you want as a data center operator? You would want the microservice to only perform its main logic. So you want that blue portion to extend all the way to the top. Instead, we see that most cycles are spent in this yellow portion, which we call orchestration overheads. These are mundane operations, like say when a microservice gets a data element from a request, it first needs to process it by performing operations like it needs to decompress it, deserialize it, de-encrypt it, and so on, before it can even perform its main microservice logic. So not only are these orchestration overheads significant, but they are also common across microservices. So let's consider one of these machine learning heavy microservices, right? Something like, say, Facebook's newsfeed microservice. Now, with several architects building a machine learning inference accelerator these days, now let's say we take one such accelerator and we allow it to completely optimize away Feed's inference operation, we are only going to improve Feed's performance by about 40% because of all of these orchestration operations. So there's only so much benefit that these inference accelerators that people have been developing can even provide in a data center. And so this is yet another classic example of how everybody knows about Amdahl's law, but also everybody forgets about Amdahl's law all the time. So in this graph, we went on to break down these different orchestration operations into underlying operations such as these sending and receiving an IO request, processing the IO, compressing the data element, serializing the request, and so forth. So note that the prediction and ranking that I've included here, it is to be considered as a part of the core application logic, but I just wanted to draw out the differences because I just talked about this machine learning inference accelerator. Now, the first important observation we make is that not only do these microservices have high orchestration overheads, but the orchestration overhead is actually common across microservices. So for example, several microservices, they spend a significant fraction of their cycles in sending and receiving IO operations, as well as in operations in dealing with that IO request. So for example, they spend time in compressing and serializing this IO request. This means that all of the hardware customizations that we have been developing so far, targeting just this main microservice logic, that's not going to improve performance by a great extent. Instead, accelerating all of these underlying orchestration overheads, now that's going to have a greater benefit as they will improve the performance across the global data center fleet by accelerating not just one microservice, but several microservices that they are common amongst. So additionally, we find that even among these common orchestration operations, right, there are actually even further lower level primitives that are common even amongst these orchestration operations. So for example, in this graph, I'm showing you the cycles spent by the various orchestration operations on this low level memory copy primitive. So for example, with Facebook's newsfeed microservice that I'm highlighting here, we see that memory copies are common across the different types of orchestration operations, like say serialization and IO processing. And so optimizing these lower level primitives like these memory copies, now that has the potential to optimize these common orchestration operations across the board, across these different Facebook microservices. So apart from memory copies, we also identified other low-level primitives that are common across these orchestration operations. So for example, in this graph here, I'm showing you how the different types of memory operations, kernel operations, data compression, hashing, and synchronization operations, how they can consume a significant fraction of the global data center cycles. And also, again, like with the memory copies, we find that they are common across these orchestration operations. So going after some of these low-level primitives can result in significant wins at hyperscale. So for example, several microservices spend a significant fraction of their time in memory movement, allocations, even freeing memory takes up a significant chunk of the global cycles. So optimizations like say a wider SIMD unit or processing in memory like you were talking about before, they can improve these microservices. Similarly, several microservices also spend a significant fraction of their time in kernel operations. For example, they spend a bunch of time in context switching because, like I said before, we're still accessing all of these IO devices via these legacy software stacks, which involve context switches and microsecond scale penalties. So again, now there is a real need for future research that can minimize the number of context switches, reduce the penalty we pay for a context switch, or come up with a hardware architecture that eliminates the need for context switching in the first place. We also perform a detailed breakdown of each of these lower level primitives that you can check out our ASPL paper for more details about. And also we went down the path of trying to find out how the IPC scales even across these lower level primitives. And we find that they don't actually scale well across different processor generations. So in this graph here, I'm showing you the data for 3 successive processor generations used at Facebook. Unfortunately, I'm not able to divulge more information about the skew for each of these processor types. So to run the microservices that we were studying, from the x-axis on this graph, which is the per core IPC, we see that the per core IPC actually does not scale well for some of these lower level operations, like say memory copies across these different successive CPU generations. So again, that reinforces the need for why we need to rethink the hardware architectures for them from the ground up. So I have very detailed breakdowns that I don't have the time to show you. But the main takeaway is that we need to not only accelerate this main microservice logic, but also all of these orchestration overheads by accelerating some of these lower level common primitives to improve the performance across the global fleet of microservices. So really, to answer our earlier question of what types of operations transform data frequently, we find that these orchestration operations, and particularly their lower level primitives, they are the ones that are transforming data very often, and they are the ones that deserve perhaps to be ossified in the hardware. So then we went on to model how to build an accelerator for these orchestration operations that frequently transform data. So yes, we need to accelerate some of these lower level orchestration operations, sure. But you might say, well, yeah, but why can't we just use an existing hardware accelerator to solve the problem, right? After all, people have developed accelerators ranging all the way from encryption and compression to machine learning operations, and even accelerators for regular expressions, right? So the answer to this question is that it's actually challenging to build accelerators for each of these orchestration operations. And the reason is twofold. So first of all, building a custom platform for each orchestration operation it's not going to be this cheap endeavor. So let's say you have 11 different types of orchestration operations, right? What are you going to do? Are you going to throw 11 different types of accelerators at the problem? No, this is going to be challenging because data center operators would really like to have homogeneous hardware resources. They want this nice uniformity because you get this procurement advantage of buying hardware in bulk for wholesale prices. And you also don't have to develop, deploy, and test on a whole host of different platforms. So really, we need to think very carefully about how should we even architect hardware for some of these orchestration operations. Now, the second reason is that some of these existing accelerators, they don't particularly work well in production. So for example, I had some really interesting experiences at Facebook when we were trying to deploy this new accelerator to optimize away some of this encryption orchestration overhead. And the hardware vendor had promised us some fantastic gains. So we said, that's great. And we went ahead and we bought some of these hardware devices and we started offloading these encryption operations to them. But surprisingly, we found that this new encryption accelerator not only did not meet the promised performance gains, but it actually deteriorated performance because the hardware vendor had only focused on improving the accelerator's performance and had not considered the end-to-end overheads that come into play, particularly from the microservices software interactions with the hardware, like say from the offload preparation time, the context switch penalties that we were talking about before, and so forth. Additionally, several of these orchestration operations, we find that they typically deal with really small granularities of data that it doesn't make sense to offload in the traditional sense of the word offload. So for example, in this case, in this graph that I'm showing you on the right here, this is a CDF of the range of bytes that were encrypted by Facebook's caching microservice. So from this graph, you can see that a good, I would say 90% of the data that gets encrypted by Facebook's caching microservice is actually really small. It's somewhere between 64 to 128 bytes. So by the time you take this PCIe accessed encryption accelerator and then you offload this really small amounts of data, the cost of the offload itself is so high, it can eat into the gains that you can get from the accelerators and also end up degrading your performance. Now you can say, well, why not try batching these encryption requests? And we did try some of these optimizations as well, except that the moment you started batching, now that is going to violate the individual requests service level objectives, because remember, some of these microservices are operating at the scale of hundreds of microseconds response latencies per request. So again, it's a very challenging problem. So now think about all of the effort that went into making this encryption accelerator, right? The hardware designers had to design the hardware, they had to test it under various scenarios, and the data center operators, they had to spend a bunch of time and money in trying to deploy that hardware, which at the end of the day did not even meet expectations. So we need to realize early in the hardware's design phase, whether this piece of hardware is going to be even worth deploying, not after designing and deploying the hardware. So to identify these performance bounds early in the design phase, we need to analytically model the overheads that arise from the microservices interactions with the accelerator. Now, such a model must first of all be simple and easy to use so that it can quickly discard all of these bad accelerator design choices early on, and it can somewhat point us and orient us in the right direction in terms of what's even the most viable type of accelerator that we should be thinking about. And second, it must still be fairly accurate so that we can still make these well-informed hardware investments before we go on to design the hardware. So to achieve this balance, we propose this analytical model, which we call Accelerometer. This model consists of an abstract system of a host communicating with an accelerator via this interface. So Accelerometer models the various types of hardware acceleration strategies like on-chip, off-chip, and remote offloads. It can model the microservice software threading designs that can be used to offload. Like say the microservice can communicate synchronously versus asynchronously with an accelerator, wherein a synchronous communication is where the host will wait until it receives the accelerator's response before it can proceed with further operations. And an asynchronous offload is where the host can just continue with further operations immediately following this offload to the accelerator. Now, Accelerometer considers offloads which can be pipelined or unpipelined, and it models both the throughput and the latency performance metrics. So let me show you a simple example of the overheads that come into play when you are offloading to an accelerator synchronously versus asynchronously. So to describe a synchronous offload, right? Let's say your host is executing along and it executes, say, C cycles in 1 second. Now, based on Amdahl's law, we all know that the C cycles can be divided into the portion that needs to be accelerated, which in our case, it will be the orchestration overhead and some of their lower level primitives, and the portion that we're not accelerating for now, using this constant alpha, whose value is less than 1. Now, if we were to execute these orchestration cycles on an accelerator that has an acceleration factor of A, the cycles spent on this operation, that would be decreased by A. Now, unfortunately, what happens is that most speed up estimates, they stop right here. And they report the speed up based on this new accelerated value. But there are actually several other overheads that show up. So to give you some examples, right? The host needs to spend some cycles in preparing the offload. Offloads can have a queuing delay of queue cycles when you're waiting for the accelerator to become available. And then there's the offload transfer latency itself. You incur these overheads for n such offloads in that time duration, and you end up with all of these overheads affecting your speed up. In contrast, with the asynchronous offloads, the cycles spent on the accelerator, they do not critically affect speed up because the same asynchronous thread can continue processing successive requests on the host CPU. But now we might, on the latency path, we might now face an additional context switch penalty of say 0.1 if a different thread decides to pick up the response once it comes back from the accelerator. So now that was just a simple example that I showed you, but Accelerometer models various other overheads, like what if the microservice must await an acknowledgement from the accelerator, which in the case of PCIe can again add to the latency. What if the offload, what is the offload size? So we saw with the example of the encryption granularities being small and how that can make a difference. So how does this now affect the offload preparation time? How does it affect the transfer latency? And then what if there are multiple threads in the case of asynchronous offload, right? And what if all of those threads are context switching? And we know that these context switches can potentially be very expensive if they occur in the critical path of execution, because they can add 5 to 20 microseconds for every single one of these context switches. So we can also use Accelerometer to model throughput improvements while ensuring that even if the latency becomes worse, its constraints are still met, which is one of the most important criteria to consider for data center applications. So we validated Accelerometer in production retrospectively by comparing the model's estimated performance with the performance that were achieved by accelerators that we had already deployed in production. So we validated against an on-chip encryption instruction, an off-chip encryption ASIC, and a remote machine learning accelerator. And we modeled each of these different dimensions. So to give you one example, in the case where we considered an off-chip encryption accelerator, we considered one that operates asynchronously. So in this asynchronous timing diagram, I'm showing you the values for each of these model parameters that we were able to determine using device specification sheets. And we've also built and open sourced a set of micro benchmarks to estimate some of these parameters. So note that several of these model parameters, like say the network traversal times, once you calculate them, they can actually be used in the context of different accelerators, as long as your data center's setup does not vary too significantly. So using Accelerometer's asynchronous speedup equation, we estimate that accelerating these encryption operations that can speed up this cache microservice that we had deployed this accelerator for by about 8.6%. But in reality, you can see that the encryption accelerator indeed improves the encryption portion of the secure IO operation, thereby improving the net speedup by about 7.5%. So across all of these case studies, similarly, we find that Accelerometer estimates the speedup fairly accurately and gives us a step in the right direction in pointing out what are some bad accelerator choices versus good ones, and then drives us in the right direction towards making reasonable hardware decisions. Okay, so now that we know that Accelerometer works well in practice after we did this validation, we are now in the process of using Accelerometer to identify how do we now build hardware for some of these lower level software primitives that frequently transform data. So I'm actually excited to tell you now about some of this future and ongoing research actually, where we identified that some of these compression and encryption operations, which are putting a lot of pressure on the caches. Yes, we want to reimagine the cache hierarchy. Yes, we want to reimagine the accelerators, but actually some of these operations, they don't even deserve to be cached. So yeah, let me get to that in a bit. Yep. So to build these data-centric hardware architectures, right, there are several research thrusts that our lab has been working on. So first, to identify what even needs to be ossified in the hardware, we are going after some of these lower level primitives, like say memory copy, that are common even across these common orchestration operations performed by these data center applications. So we have been identifying, like you said, these microarchitectural bottlenecks that are common across them. And we're trying to reimagine what the hardware architecture should even look like for them. So one of the things that we really found out is that for several of these remote procedure call operations, compression operations, serialization operations, encryption operations, particularly ones that are a part of this IO path, they actually involve single-use data accesses and single-use data copies, implying that there isn't really a need to even bother caching such accesses in the first place, because it's not like it's a hot region of data or anything. It's just getting copied into the kernel buffer this one time, and then it's getting sent off to some other microservice, or it's getting sent off to some other accelerator or something. So we think that there's no need to even bother caching such accesses and waste cache utilization in the process. So a cache that's able to, for example, intelligently bypass such accesses is an example of one such optimization. But there's also other things that, it could be a part of the hot path that it does deserve to be cached, in which case we are trying to figure out how we should even reimagine the memory hierarchy for these operations. So this is work that is currently ongoing, and we're hoping to have a chip tape out at the end of the day that serves as an SoC for some of these lower level primitives. So next, we find that with these data movement overheads, there's actually a lot of redundant data that's just floating around, which could easily be eliminated by incorporating ideas involving near memory processing. Except we want to do this a little bit differently, where we want to peek into the data and understand what the data is all about so that we can more efficiently use the capabilities of near memory processing. So for example, several fields of RPC messages in interfaces like say protobufs, they have common values across messages. So for example, if there's a Boolean field that says whether a user who sent the request has been authenticated or not, then more often than not, that field is going to be true rather than false. And yet we keep bringing in the same Boolean information over and over again, and we keep performing all kinds of data transformations on these protobuf structures over and over again. So in this particular case, for example, we have this ongoing project where we are interested in bringing in ideas that are more commonly used in software engineering. So ideas around fuzzing, where say we always cache those RPC fields that are common across requests. And then we use near memory processing to compute the partial mismatches across these protobuf fields so that we can selectively bring them into the caches. So that's just one example, but more broadly, instead of behaving in this data agnostic way, we are going after analyzing data and analyzing program behaviors to really take advantage of near memory processing in a more efficient way to design these data-centric hardware architectures. And again, this is work that we currently have going on. So apart from near memory processing, another way to capture diverse data orchestrations in a more generalized way is to explore a reconfigurable memory hierarchy that captures regular and irregular access reuse and can perform decoupled data orchestration to hide latency in a more cheap way. So for example, this could now mean having storage elements that can be repurposed as data structure specific caches or scratch pads. And maybe you can have reconfigurable interconnects that provide efficient marshalling of data depending on which system elements you want to send the data to. And next, it is insufficient to just stop at the hardware layer. I didn't get a chance to really talk about this during my talk, but another thrust of my research is to focus on software abstractions and frameworks and virtualization layers. So we really want to build operating system and abstraction layers for this new data-centric hardware architecture. And we don't want to do this in a way that it's like an afterthought to the changes in the hardware and the application primitives, which is what it's mostly been like today, where every time a new accelerator comes out, we see that people are spending order of months to years just building these highly optimized system stacks for each of these new accelerators. So now that we have an understanding of these lower level common primitives, we are interested in building a taxonomy of them and identifying how they're accessing data, for example. And then we're interested in building these composable operating system and abstraction layers for each of these hardware primitives. So we're hoping to bring in ideas from the programming languages community here to see, for example, whether we can apply program synthesis to build some of these composable software layers so that tomorrow, whenever a new hardware unit comes out, it's just going to be a matter of software exploration to figure out which of these software abstraction modules you want to piece together and compose them to create the entire software stack. So finally, we want to build upon all of these ideas to go after our final objective of building this homogeneous API all the way from the edge device to the edge data center to the backend cloud. So the key insight underlying this idea is that these data transformation operations, right, they are actually present across the entire spectrum from the edge to the cloud. So we are interested in seeing to what extent can we even make the fundamental architecture homogeneous all the way from the edge device to the edge data centers and the backend cloud, while still supporting this wide range of underlying microarchitectures, which possibly have different constraints in terms of performance, power, and cost. So this will enable other important attributes, like now you can have uniformity in abstractions, you can have uniformity in programming primitives, and this will make it easier for just software development across the board. That's my talk. Thank you for your time, and I'm happy to take questions.